Hello everyone. Today let's solve the problem Bicolorings, right? So this was asked in the educational code forces round 51, rated for the division 2. So you can just go through the question. I'll just summarize the question so that it will be easier for us to solve the problem, right? So what the question states here, we have to just give me a second here. 1 second. Yeah. Uh, we have to count the number of ways to color a 2 into n grid. So we have to count the number of ways to color 2 into n grid. Just remember this one, right? So each cell, either it can be black or white, right? Such that the graph of same colored adjacent cells has exactly k connected components. So this is very important, right? So we have to count the number of ways to color a 2 into n grid such that the graph of same colored adjacent cells has exactly k connected components, right? So two cells are neighbors. So here two cells are neighbors if they share an edge that have the same color. If they share an edge or the vertices or the vertex of the same color, we have to output the count modulo this one, the value modulo value they have given here, this one. See here, this one, let me not write this one, instead I'll just go with this one, 9982 44353. This is the modulo value. We have to output the count modulo this value, right? So this is fine. So constraints we have been given, this one, n less than or equal to n greater than or equal to 1 and less than or equal to 1000, and k less greater than or equal to 1 and less than or equal to 2n, right? So this is fine, and we have to output the modular value this one, that one also we have to keep in mind. So let me read the question one more time loudly, just try to understand this one, man. We have to count the number of ways to color a 2 into n grid. When I say 2 into n grid, each cell black or white such that the graph of same colored adjacent cells has exactly k connected components, right? Two cells are neighbors if they share an edge and have the same color. We have to output the count modulo this one, value this one. This is fine. So let me remove this one entirely, man. This is fine. Now let's do one thing. Um, hmm, this is fine. So let's go with the approach. So I hope the question part is completely clear, right? So I hope the question part is completely clear. So here we have 3 and 4. The output that we need to get here is 12, right? So we have the 4 and 1. So the output that we need to get here is 2, right? So just give me a second, 1 second here. And we have 1 and 2 here. The output that we need to get here is 2. So I hope the question part is completely clear along with the input output. Let's do one thing. Let's quickly discuss the this one approach followed by the complexities, and then let's write the code. As usual, first let's discuss the approach. So here I have considered the same first example that they have given in the question. So I can just try to implement the same thing for the second, third, or the fourth example in this case, right? So let's go with the first example for the approach. So we have considered 3, 4 here. So output that we need to get here is 12. Basically, this is the output part, right? So this is fine. So we will be making use of the dynamic programming or the bit mask DP, right? So bit mask dynamic programming. This is fine. Now let's move on with the detailed explanation or the step-by-step explanation. Now we will be using the 2-bit masks for the column, right? So again, we use 2-bit masks for the column, right? So 0, it is equivalent to WW. So this one WB. So here this one 2 is equivalent to BW and 3 is equivalent to BB. Just remember this one, right? So why we will be making use of the 2-bit mask for a column, right? So 0 for WW, 1 is equivalent to WB, same goes with 2 and 3, BW and BB. So initial components for the column, nothing but the this one column only. I'm considering the first column only, right? So just give me a second here, 1 second. So yeah, let's go with one column only here. So we'll be going with a column 1. So here initial components for column 1, actually it has to be column 1, not just for the column. So low of 0, this one we will be considering basically whatever this one, what do we call WW of 0. So not the low of 0, WW of 0, because 0 is equivalent to WW, 1 is equivalent to WB, and BB is equivalent to 3, and 2 is equivalent to BW. We are considering only the column 1, right? So here we have considered WW, BB, uh, WB and this one BW of 2, this one 1 3 and 0, how it came, so here from this step, right? So this one BB, so this one, this is fine. WW, this is fine. WB is nothing but this one, and BW is nothing but the value 2, right? So I hope this part is clear, man. Easy to understand, right? So we are just going with the initial components for the column 1, right? This is for the first column only, or the one column only. Now, so WW of 0, we are considering only the vertical cells, right? So vertical cells are same. There is only one component. So DP of 1 0 will be 1 here in this case for this one. So BB of 3, what we will be considering. So here also it will be one component only. So DP of 1 3 1 will be 1 again, right? So WB of 1, this will be top is not equivalent to bottom, or top is not equal to bottom, so we have to consider two components here. DP of 1 1 and 2, that is also equivalent to 1, and finally BW of 2, so we have to consider two components, DP of 1 2 2, which is equivalent to 1 again. So I hope this part is clear, right? So next let's move on with the next step, man. So we will be going with a transition matrix in the sense, so this is nothing but add of previous current, right? So this we will understand it crystal clear when we write the code basically. This part I'll just show the transition matrix for the approach. So when I say add of previous current, so we are going with, or we are finding how many components the new column adds when it is appended, right? So when it's appended, right? So current we are going with 0 1 2 3, and the previous we are going with 0 1 2 3, nothing but WW WB BW BB, this one we know. So this will be 0, 1 at triple one, 0020, 0, 2 double 0, 1 1 triple 1 0. This is just for the reference for now, right? Just keep this in mind. You can just pause the video and take a look into it, right? So next, let's move on with the next step, man. So now, just give me a second. Yeah, now we are considering this one from column 1 to column 2. Nothing but here in this case, we are, or we have to compute DP of 2 here, right? So we have to compute, or we are computing the DP of 2 here, right? So this is fine, man. So we have to apply every previous mask here. Meaning this one PM is nothing but the previous mask to the current mask. We have to apply every previous mask to the current mask, right? Current mask, then the new components becomes previous of C plus add of previous mask and current mask, right? So this will result in non-zero DP of 2 entries. So when we mask this one, we are masking C to count, right? So this one W of 0 0, previously you can just look into it. So we have 1 to 1 and 2 to 3. See here, we are going with the C to count, right? So 1 to 1, 2 to 3, WB of 1. So this will be 2 to 3 and 4 to 1, right? So 2 to 3 and 4 to 1. Same goes with other two as well, right? BB and other one is left. So just give me a second here. This one will be 4 to 1. Just for the reference, just look into it. BW of 2 is 2 to 3 and 4 to 1. BB of 3, so C to count, so this one 1 to 1, this one 2 to 3. So this part is fine. You can just pause the video and have a look into it again, right? So this is fine, man. Now we are done with the column 1 to 2. Now let's go with the column from column 2 to column 3. When I say column 2 to column 3, we have to compute, or we are computing DP of 3 here. We are computing DP of 3, right? So we only care about the final K equals 4. In the input we have been given K equals 4, right? So here this is nothing but the K. We only care about the final K equals 4, right? So here we have to calculate the DP of 3. Sorry, where did it go? Yeah, DP of 3 here. We only care about the this one, final K equals 4. So after propagating DP of 2 through the same transitions, the count at the column 3 that have exactly 4 components are this one. DP of 3, I have considered this one directly. You can just have a look into it. DP of 3, WW of 0. Same thing goes with the other 3 as well, right? So the output that we got here is 2, 4, 4 and 2, right? So this one we have to sum up. So we will sum over, or we will sum up final masks, in the sense we will sum over final masks, right? So total we have got here 2 4 4 and 2. So when we sum up 2 plus 4 plus 4 plus 2, so this will lead to 12 basically. encapsulate to 12. So this is the final output that we got here. So the output that we got here, this one we will return basically. So this one we will return this one as output, right? So the output that we got here is 12, which is equivalent to the output that they have mentioned for the example one within the question. So our approach works absolutely correct in this case, right? So our approach works absolutely correct in this case, right? So I can just show you the concrete enumeration as well. Enumeration in the sense all the 12 mask sequences that yield 4 components. It has to lead to 4 components, right? So k we have been given 4, right? So k we have been given 4. So I can just show you this one, all the concrete enumerations in the sense all 12 mask sequences that yield 4 components. I can just write it over here. One is ww wb bw. This is the first one, right? Second one is ww, same thing. This one bw wb. So this is one of it. This is one of them, right? So third one is we can consider wb wb bw. This one also we can consider third one. Fourth one is wb bw as well as ww, the fourth one. Fifth one is wb, this one bw and bw. This is fifth one. Sixth one is wb, bw and bb, right? So just give me a second here. What happened to this one? 1 second. WB, BW, and BB. So this is fine. Now the seventh one is BW, WB, WW. Next one will be, eighth one will be BW, WB, BB. So these are first eight I have written. The last four, let me show this one. However, I have written all the eight. So almost eight, sorry. So it is 12, right? So we are going with all 12 mask sequences that yield 4 components, right? So this one, the last four, let me write this one. The ninth one will be BW, WB, and BB, right? So the 10th one is here BW, BW, and WB. 11th one is BB, WB, BW, and the 12th one or the last one is nothing but the BB, BW, WB. This is fine. So these are the 12 mask sequences that yield 4 components. Means these are the exact column mask sequences, nothing but column 1, column 2, and the column 3 that give total components that is equivalent to the 4. Right? Just for the reference I have written, so you can just have a look into it. You can just pause the video and you can have a look into it. So the final output will be, we have to return this one actually. Total we need to return. So output that we got here is 12, which is equivalent to the output that they have mentioned for the example one. Now I hope we are completely clear with the this one approach part, right? As we are completely clear with the um, approach part, so we can just move on with the this one. What do we call uh, complexities part, right? So let's quickly move on with the complexities part. Just give me a second here. 1 second. Yep. So what will be the time complexity here? The time complexity would be because of n square. So why it is n square? So basically it is because of n into 4 into 2n into 4. So overall it will be because of n square itself. So more precisely if you want to write, so it will be because of n into max c, nothing but the max column, into 16, right? Why it is because of n into max c into 16? Because for each of n columns we are iterating over 4 previous masks, right? So that I showed in the last step, up to 2n component values and 4 next masks as well, right? So this we know. So overall time complexity would lead to big of n square. So what will be the space complexity here? The overall space complexity would lead to big of n square as well. Precisely it would be big of n into 4 into 2 to 2n basically, right? So again, so it will be big of n square for the DP array, nothing but about it is equivalent to the 8 into n square bytes per int constant factor, right? So overall space complexity would lead to big of n square. So the time complexity and the space complexity for the code that we'll be writing in the future would be big of n square and big of n square respectively, right? So now as we are completely familiar with the approach and the complexities, we are good to write the code. Let's start writing the code. So let's start writing the code. I'll just come to the compiler here. First, we'll be going with a fast input output. We need input output package. So I'll just go with java.input output.star, and also I'll be going with this one different utilities. I'll just go with java.util.stuff. So this is fine. Just give me a second here. 1 second. Yep. Now let's go with a class main. So I'll just go with public. So class, I'll just go with main as usual. You can just give any class name that is relevant to the problem. Right. So this is fine. Now let's go with a modulo value, man. They have strictly mentioned in the question, right? So let's go with a modulo as required. So I'll just go with static here. So this one final int. So I'll just give a mod here. This one, let me copy paste from here itself. So let me copy this. Let me paste it over here. So this is fine. Now let's go with the main method, right? So this is fine. Uh, Let me go with throws exception, or else we'll be getting the error. So I'll just be going with throws exception. So this is fine. Now first let's go with the fast input reader. Nothing but buffered reader. So this one br equals new. Let me go with the buffered reader new. So this one will be uh, input stream reader. So this one will be system dot n. So this is fine. Now let me tokenize the single line input. In the sense, let me go with the string tokenizer here. String tokenizer st. So this one equals new string tokenizer. So this one will be buffered reader dot read line. So this is fine, man. So the next step would be we have to read n and k, nothing but columns and the required components, right? So they have given n and k in the input itself. So see here, this one 3 and 4. So that itself we have to read n and k, right? Nothing but columns and required components. So both are integers here. So this will be integer dot pass and string tokenizer dot. So this one will be next token. This is fine. So let me copy the same thing for k as well. Let's change the variable name. So I'll just come here. This one is fine. Now let me give k here. This is also fine, man. So let's do one thing. Let's quickly compute and print the answer using the bitmask dp function. Right. So let's do one thing here. Hmm. So let's do one thing. For the calculation part, let's make use of another this one. For the bit mask, we have to go with the masking, right? So as per the approach, we have to go with the bit mask or masking basically. For that, let's make use of the helper method solve here, and then we can just make use of the this thing. What do you call basically uh, that solve method within the main method, right? So I'll just write here print writer first. Let me give here print writer out equals new print writer. Let me call here system dot out. This is fine. This is fair. So next we have to print from the solve method. So I'll just consider this one solve helper method here. Then we can just make use of it within the main method. So let's do one thing. Let's solve basically this solve method what we are writing. This will be using the dp over columns dynamic programming, and also it masks from 0 to 3, nothing but 4, right? So 4, it masks 0 to 3 and the component counts from 1 to 2n. This we know from the approach. Let's try to do the same thing here. So this one will be static integer int solve, right? So I need the parameters n as well as I need the parameters k here. So here this one has to be int n and int k. So this is fine. Now within the solve method, uh, let's go with the maximum possible components, that is 2 into n, right? So this we know. I'll just go with the maximum possible components. So here this one will be uh so I mentioned this one as column earlier, I guess. So just one correction, this is nothing but the maximum components, not the column. So this is fine, man. Now we have to go with the dp of I mask and see, nothing but here we are dealing with a number of ways to color first I columns, that is ending with a column mask, nothing but mask and the total component c. So we will be going with the dp array in short basically. So I'll just go with here dp that is equivalent to new int. So let's initialize this one with n plus 1 for 3 arrays we have considered, right? So this one will be max components max c plus 1. Fine. Now we are done with this part. Now, as per the approach, the last part, we have to go with the base initialization for the column 1. I showed you this one step by step. 0 equals ww, 1 equals wb, 2 equals bw, 3 equals bb. Not the last part, but the first step basically within the main this thing. What do we call within the approach, right? So we have, let's go with the base initialization for the column 1. So this one will be dp of 101, right? So three as we have considered, right? So all of them we went with 1, right? If you remember. So this one, let me copy the entire thing and paste it 3 times and make the necessary changes. So this one will be dp of 1. uh this one will be 3 1. So this one will be 1 uh 1 2. So this is also fine. The final one would be dp of 1 2 2. This is also 1. This is fine, man. Now let's go with the pre-computed added components when transitioning from previous mask to the current mask, right? So nothing but when transitioning from the row to column in simple terms, right? So we have to go with the add of previous mask and current mask. Nothing but in the approach, I said the same thing. So we are dealing with how many new components appear when appending current mask after previous mask, right? That's what we will be doing. So in simple terms, so we will be going with the index mapping. 0 equals ww, 1 equals wb. I showed this one in the approach, right? So 2 equals bw and 3 equals bb, right? So let's write the same thing. This one will be int add equals, so within this square braces, so this one will be 1 0 1 1 1. This one I showed, right? So I just asked you to pause the video and look into it. You can just go and look into it, right? So this is for ww basically, right? 0 1 1 1 because ww wb bw and bb, right? So 0 triple 1. So next, uh let's go for this one from wb, in the sense, if you remember, it was 0020, I guess, right? So 0020. This is fine. Next, it would be 0200 from bw. So this is from bw, so this one will be 0200. This is fine. Finally, so we will go with 1 1 1 right? So this is fine, man. One, the last value is 0. So this is from bb, right? So this is fine, man. So let me come out of this one entirely. Now we are done with this one. We have pre-computed added components when transitioning from row to column successfully. Now what we will do, we will iterate the columns 2 to n, and we will be filling the dp, right? So we'll 3 arrays we have considered. So let's consider the 3 for loops here. So many for loops I have to consider, man. So we have to iterate columns from 2 to n2 just to fill the dp. So this one we know. So I have to write this one, right? For loop. So this one will be int I equals to I less than or equal to n. So this one will be I plus plus. From the this one, basically we are iterating the columns from 2 to n, and we are filling the dp, right? So let's go with the previous mask as well. So for the previous mask, I'll just go with int pm is nothing but the previous mask, that is equivalent to 0, previous mask less than 4, and finally previous mask. Let's increment this one. We have to move to the next one, right? So this one is fine as well. Now let's go with one more for loop. So we have to iterate the existing component counts from previous column. So this one will be again for int c equals 1, c less than or equal to max c, and finally c plus plus. So this is fine. So within the for loop, what we need to do first, so we have to go with the number of base for I minus 1 comma previous mask and C. So this is int base equals, so dp of I minus 1 pm. So this one C. Right, so this is fine. We are just going with the number of ways for I minus 1 pm. See, so let's go with a simple if condition here. We have to skip the 0 entries to save the time. So if ways equals 0, so then we need to continue. This is fine. Now let's do one thing. Let's try every current mask, nothing but the this one cm, right? So let's go with one more for loop here. So this one and current mask equals 0, current mask this one less than 4, current mask plus plus. So within this for loop, what we have to do, the same thing, we have to go with the new component count after the transition, nothing but here new component, nothing but nc here. This one let me assign to the c plus add of previous mask current mask as per the approach. So whatever we have discussed in the approach, exact same thing we are articulating in the form of code here. So this is fine. Now let me write the simple if condition. If the new component is less than or equal to max component, so max c, then what we need to do, we have to add the base into the we have to add the base into the dp of I current mask and the new column with a modulo, right? So this one has to be dp of I current mask, so new component, so this one is equivalent to uh, dp of I, so this one, one second, one second, yeah, this one has to be dp of I current mask and new uh, this one new component as well we have to consider, right? Also we have to go with the number of base or nothing but base. So as we are considering the mod value, let me give mod here, modulo mod. This is fine. Let me come out of this one entirely, man. Yeah, this is fine. Now we are left with we have to go with, or we are left with summing all the ways that end at the column n with exactly k components. Let's write this one quickly. So let we have to store somewhere the result. So I'll just go with the answer. Let me go with 0 here. Let me go with one for loop here. This one has to be int m equals 0, m less than 4, and let me increment the m. So this is fine, man. So let me go with the if condition here. If k less than or equal to max component, so this is nothing but the safe check. When I say safe check, so we are going with a k that is guaranteed, right? So k that is guaranteed has to be less than or equal to 2n, right? According to with the constraint, right? So this is fine. Now within this if condition, let me give answer equals answer plus dp of nmk we have to go with, right? So this one will be n, this one will be m, this one will be k. This is fine, man. So finally modulo, so this one will be mod. So finally what we will do, so we will go with the answer. So I'll just go with the return answer. This is fine. We are done with the coding part. We are done with the coding part. So this is fine, man. We're done with the coding part. So we haven't mentioned the main method within the this one, right? What do we call? Uh, we haven't mentioned the solve method within the main method, right? So we have made use of the helper method solve for the masking purpose. So next we have to make use of it within the main method, right? So where I have made use of this one solve. Yeah. Now let me copy this one. So here I had stopped here within the main method. Let's continue the same. We have two lines of code, man. So we have to print the final result, right? And flush, right? So that's what we need to do. Flush or close, right? So let's print the final result. So this one will be out dot println, as we are making use of the print writer. So let me make use of the solve here. What are the parameters basically? We have input n and k. Simple. Next, let's flush, or you can just go with the flush or close, both works. Sorry. Sorry. Yep, this is fine. Now we went with out.flush here. You can just make use of the flush or close. This is fine. Now before checking the code with different inputs, so let's do one thing. Mm, Let me copy paste the signature starter template. Just give me a second here. So I'll just come here. So yeah, let's focus on the logical part here. Let me come here. This one, let me copy the input. The output that we need to get here is 12. Let's check. Mm, st double dot I have given here. So this is wrong, man. Line number 28. So this one has to be single dot actually. String tokenizer dot next token. So let me run this one again. So yeah, this was the only mistake. Now we are getting the correct output, right? So this is fine. Now let me go with the input one. So this one 4 and 1. The output that we need to get here is 2, right? So this is fine. Let me copy this one and paste it over here. So we are getting 1 instead of 2. So somewhere we have done something wrong then. So let me check the third input as well. We have to get output 2. We are getting 2 for this, 1 and 2. So 4 and 1 we are getting 2. So we are getting 1 for this. We need to get output 2, right? So let's check what we have done wrong. Let's check. So what mistake I have done here is in the line number 46. So this one we are going with a DP transition, right? So DP bitmask DP transition. Here for the row WW I have considered this one. We have to consider or we have to go with 0 triple 1. Instead I have went with 4 ones here, right? So this has to be 0 triple 1 for the row. This one WW basically for this one is first one is WW, right? So if you remember the approach, you can just go uh, to the video to the approach basically and check. So this is for the row WW double W basically. So here it has to be 0 triple 1. So instead I have given 4 ones. So that is the reason I'm getting 1 here. So let me check now. It has to give 2. Yeah, now this is giving us the correct output basically, right? So we are getting the correct output for the 3 examples that they have mentioned in the example, I mean within the question basically, right? So this is fine. Now let me copy this one entirely. So let me come here, let me hit the submit button, man. So let's wait for some time. Let me paste this one over here in the submission part and let me hit the submit button. Simple. Let's wait for some time. Let's wait for some time. Just give me a second. So here you can clearly see in the verdict or in the toast it is showing accepted. Also in the verdict we are getting accepted. This is fine. So you can clearly see here we have made use of the pure dynamic programming here, bitmask DP, right? So along with the bit masking or masking, right? So we have went with the bitmask DP here just to solve this particular problem. I hope the solution part is completely clear, man. This is going to be the last problem on the this one, bitmask DP. Right, so next we'll continue with solving the dynamic programming problems. So next it will be dynamic programming on the trees basically. So let's solve some 1 or 2 problems basically, very good problems on trees, how to apply DP on the trees basically, right? Let's see that. Right. For now, this is going to be the last problem on the bitmask DP. I hope the concept is completely clear, man. Initially, we went with simple DP problems. We saw 1D and 2D DP, right? So now um, we have solved some of the problems on bitmask DP. Right. Next, we'll be solving dynamic programming on the this one trees. Right. So I hope this part is completely clear. You have understood the concept of bitmask DP masking, right? Masking part basically, right? So this is it for now. Thanks for watching, guys.